folks. Welcome to Rational Science, directly from Frankfurt, Germany. Anyways, we have a long day today, so maybe you have the patience to stick around. We'll be talking about first science. We have our resident critic, and I'm going to address a lot of the questions or comments that he made. I'm going to try to also address a question that was raised about 2 weeks, maybe 3 weeks ago, I forgot, which is why light bends. When it goes through a prism, it bends. It doesn't bend, like a curve. It bends sharply. And we need to find out, why that happens. And by why, I don't mean the nonsense, the poppycock of refractive index. Okay, refractive index, I've dealt with that many years because I worked in the semiconductor industry and we use refractive index every day. But refractive index is a mathematical description. That's all it is. And refractive index doesn't tell us. In fact, it's a Ptolemaic explanation for how light behaves. So we get rid of that. We don't use refractive index to explain. Okay, we cannot use that to explain what's happening physically. When light bends or goes into what they say is a denser medium. Anyways, we're going to address that issue. And then at the end, we'll have the main course, which is bonds, James bonds. What are those Jimmy bonds that they have in quantum mechanics? And so, well, let's get started. I'm going to make a little introduction because people say, Bill, you insult all those poor mathematicians from Cambridge and Harvard. You treat them very badly. You make fun of them. You treat them like clowns. And yeah, I do. I treat them with the respect that they deserve. That's the way I look at it. And, when I started like 25 years ago to get my theory out there and getting people to know the theory, just a different way of thinking, right, of how this universe works, what it is, etc. Well, I was treated quite badly. I was ridiculed and I was insulted. They just threw rotten tomatoes in my face. And, that's not what I expected, because when I was in college, I had this idea, this idealistic, naive version of what science was supposed to be, what the scientific environment was like. And I thought that when you go out there and you present a theory, people say, well, they may not agree with it. They say, well, I don't agree with it. Here's some points that I've got against it, whatever. That's not what I encountered at all. It was just ridicule and insults, the whole works. And so, in a way, it was a wake-up call for me because, suddenly I came face to face with the real scientific establishment. And, when you look at it from the days of the Greeks, they had all these schools, the Stoics, the atomists, and the cynics, and so on. And they would, laugh at each other. They would ridicule each other. So this is not something new. That's the way we humans are. And so really I was quite naive in thinking that maybe, science was something different. I had this idealistic version of science that, people were respectful and they listened to your ideas and so on. No, not at all. It's just ridicule to someone who doesn't think like you. It's like the Buddhists, they laugh at the Christians, they laugh at the Muslims. Sometimes not in their faces, but always behind their backs for sure. And so that's the way we humans are. And so if you feel that I'm mistreating the poor mathematicians, think again. And the first thing I'll tell you is go to Riverside University and look for John Baez's crackpot index. It's on that site. It's on a university site, a site that is maintained indirectly, right, by the government, because taxes maintain part of the income of that school. And so, you're paying taxes, and they use that crackpot index like they used it on me to ridicule people, to belittle them. And so before you tell me that I'm mistreating the poor mathematicians, write a letter to Riverside University and tell them to get that garbage off their formal site. Okay, that's the way it should be. Okay, so yeah, don't treat me so badly. Look around and you'll find what the real environment is in science. And another thing you should include in that is the fact that the mathematicians run the show. They have control over the whole works. They have their magazines. And what is the problem with that? Well, not only are they the editors, the peer reviewers, etc., for quantum mechanics, relativity, string theory, but they're the gatekeepers. They will not allow your theories to reach the public unless you go through them. That's where the problem is. And that's wrong because, the way I look at it, right? Why? Because if you have a theory of how the universe works, which has nothing to do with math, no equations, no experiments, you have a different theory, a different vision of how this universe works, why not have that reach the public? Why have gatekeepers? They say, oh, you got to go through math, you got to go through proof. The peer reviewers have to look at what experiments you ran, etc., etc. There are no experiments for light. There are no experiments for gravity. And I mean for the mediators. They're invisible. They're intangible. We will never figure them out by running an experiment, going to the lab, an equation, observation, prediction, all that garbage that belongs to mathematical physics. That has nothing to do with science or with physics. And so if you have a different theory, why not have the public listen to that theory? And no, they will not. And that's where the problem is. That is censorship. And you say, well, we don't want trash to reach the public. So what is quantum mechanics? What is relativity? It's trash. It's garbage. It's poppycock. What does quantum mechanics, which says that a particle can be at two places at once, that says that this particle can affect that one through what do they call entanglement without a mediator? That's black magic. How is that any better than flat Earth? How is that better than the ether is, or the electric universe, or all these other dissident groups? They're all the same. I mean, if you're going to blacklist flat earthers, why are you going to accept the garbage of quantum mechanics, which all explanations, all without exception, all explanations of quantum mechanics are garbage, are trash, are poppycock? Why are you allowing that to reach the public and not the flat earthers or whoever? I mean, for that matter, just an example. And so, yeah, I have a problem with the establishment, and I fight against them, and I hold nothing back because there's, I have very little respect for a mathematician who says that he studied 10 years in college and then tells me that gravity is the warpage of 4 number lines. Yeah. Tell me about it, okay? And so here we have this fellow, and he essentially represents the ideas of the establishment, okay? So it's good that he comes aboard and he throws garbage at me. I have no problem with that. I can handle it, believe me. And I like to answer these, the issues that he raises, because there are issues that other people, might question there and say, well, hold it, what about this about math? What about this about quantum mechanics? What about relativity, string theory, etc.? And this fellow raises those issues from the establishment's point of view. Whether he belongs to the establishment or not, I don't know. It's irrelevant. The issues he raises are all from the establishment. So let's address that. And we begin with science, okay? Science itself. What is science? What is science supposed to be? What is physics supposed to be? Okay? Let's go with that first. And he says the following. Give me a second here. He says, Bill Gaede's rope hypothesis, thread theory, right, is a non-quantitative theory. It makes no quantitative predictions. Yeah, we don't do any quantitative and we don't do any predictions, okay? Because that's not what science is about. Quantitative and predictions have nothing to do with science. What is science? Science is rational explanations. That's our definition of science. You may not agree. You may say that's not what Newton and Galileo and all these guys from the 17th century came up with. Yeah, because they didn't have the slightest clue what science was, and here we are today. We can't answer a single question of quantum mechanics, of how the universe works at the micro level, at the macro level. Why? Because these people are still doing it the wrong way. We have the wrong people researching the questions that people want answered. Everybody out there and their mother, they want a qualitative explanation. And these people are saying, well, let me give you a quantitative description of what we measured and what we proved. And here's the equation. People don't care about any of that. People want to know why this pencil falls downwards. I don't need to know any math to explain that. And that's where the problem is. Right now, you have to go through the mathematicians who are the gatekeepers, and they say, I want to see your equation. I don't need any equation. I'm going to tell you what causes this pencil to fall to the floor. That's different than saying, at what rate is it falling? 9.8 meters per second squared? Who cares about that? I mean, that's something that concerns mathematicians, not the public. The public wants to know why the baby fell to the floor and why he didn't, go to the ceiling or stay in the midair. That's what they want to know. And so, yeah, this notion about quantitative and predictions and observations, gawking, drooling. You can observe all day long and not understand anything. Does that make you a scientist because you observed? So, yeah, in science, we do not observe, we do not gawk, we do not make predictions, we do not use math, because math are descriptions. We want explanations, rational explanations. And we don't care about predictions because, that's astrology. We need explanations. Explanations deal with the past. Predictions deal with the future. Science is about the past, not about the future. Science has to explain what happened, how it happened, why it happened, what caused it to happen, what the mechanism is. That's what science, as it relates to physics, is supposed to be about. Okay, so yeah, explanations have no use for quantities or predictions. It rejects how, talking about me, he says that I reject how mathematics works. Yeah, and that includes what is it? Models, predictions, tests. Well, we do use models, but not predictions or tests. We don't have any use for tests for experiments. Experiments are there to persuade people. Experiments are there to collect evidence and persuade the jury to believe like you do. It's got to do with belief. That's got to do with religion, not with science. In science, we do not attempt to persuade people, even though it's natural, human nature to do that, right? But the science part is the objective part, where you say, this is the mechanism I propose for this, for gravity, for magnetism, for electricity. That's science, okay? That's where it stops. Whether you believe one theory or another, whether they prove one to you or the other one, that's religion. That's got to do with, Sunday school, not with science. And so he said, and what I'm saying is, what's missing in mathematics is explanations. That's what's missing there. They don't have any explanations today for any phenomenon involving invisible, intangible mediators, gravity, light, magnetism, so on. He says replaces it with scientific definitions. He didn't use the word exactly those words, but I edited him a little bit. Of sine qua non terms such as object, exist, and touch. Yeah, physics is the science of existence. That word belongs exclusively to physics. Anyone using the word exist in any way, shape, or form has crossed the line into physics, whether they know it or not. And so when people say, well, I don't know if God exists. Does God exist? Well, I believe God exists. Well, I don't believe God exists. Well, maybe he exists. I don't know what tests we can run to prove that God exists. Very simple. You have to define the word exist. Once you define the word exist, you know whether God exists or not, or whether this chair exists or not. We have to define the word exist. No one has done so in the last 10,000 years. And so, he says, oh, Bill, You're redefining all these words. It's that they've never been defined. That's where the problem is. No one defined the word object in 10,000 years. No one knows what a thing is. And you can't do physics without an object, without a thing. And no one has defined it. And I'll prove that very easily to you. Let me convince you. Let me persuade you. Let me recruit you. Look for any textbook of physics, anyone at your leisure, and show me just one book on planet Earth that begins by defining the word object. I mean, if physics can't do without object, you would think that's the first word that should be defined on the first page of any textbook. And that's not what you see out there. You don't see the word object, you don't see the word exist defined. And so yeah, I had to define those words for the first time in human history. And that's why I reached different conclusions than all these bozos, clowns from science, so-called science, mathematics, mainstream. He says, Bill says that objects demand drawings. Well, if an object is that which has shape, which is our definition, the scientific definition of an object, of a thing, that which has shape, not that which you can touch, not that which you can see, because those are irrational definitions, right? It's that which has shape. All objects have shape. And if you know an object that doesn't have shape, please let me know, okay? But if it has shape, there should be no reason not to illustrate it. And you don't have to make a perfect drawing. We just need to get a ballpark figure of what you're talking about. You know, there's a fellow was talking about the ether, and he was saying it was a thing. And I'm saying, okay, draw it. And he said, well, I can't draw it because I've never been outside of it to see it, and it doesn't have anything on the outside of it, and blah, blah, blah. All he had was excuses because he could not show me that, you know, that ether was a thing that has shape. And so, yeah, we define these words, and that hurts a lot of people. And I have a saying that the word object, the definition of the word object, destroys all religions, especially all of mathematical physics, because mathematical physics does not have a single object. And you say, what kind of physics is that when you have no objects? What are you doing physics with? What are your mechanisms with? And they say, we do math. Oh, I thought you were doing physics. No, we do math. Okay, great. Okay, so he criticizes my point of view. He says, Bill says physics is explanation only. Absolutely. Observation, measurement, prediction, and experiment are not a part of science. Absolutely. Experiments are used only to persuade people and give them an idea that that you know what you're doing, that you know how to explain. It turns out there are no explanations in all of mathematical physics. And he says, why is it wrong? Without testable quantitative predictions, any story fits. And it turns out that with testable quantitative predictions, what do we have? We have the following stories, right? The story that he tells or that the establishment tells. Gravity is the warping of number lines. Oh, great. So looks like any story fits, right? Particle can be at two places at once, quantum mechanics. Earth drags time around itself. Gravity probe B, right? Self-creation of matter at the Big Bang. Yeah, like from what? You know, I mean, how did the particles come into existence? And they say, well, you know, we have virtual particles popping in from the void, coming into existence and out of existence constantly. Yeah, by what process? Explain the process, the mechanism. Okay, don't tell me that they do. Tell me how they do it. Okay, and then planetary atom explains what? Ionization. Yeah, and that's what they use for electricity and quantum jump and all that stuff. So yeah, they have all these stories, these any story fits, and that's exactly what we have today. So I don't think that measurement or predictions or any of that changed anything. We still have fantastic stories from the mathematical establishment. Nothing has changed. In fact, they're more fantastic than the Bible. I mean, the Bible talks about Jesus going to heaven, coming back, and so on. That's more believable than saying a particle can be in two places at once. I can't even imagine that. I can imagine Jesus going to heaven and coming back. I cannot imagine a particle at two places at once. So, yeah, I guess any story fits, right? Okay, so he accuses me of doing a little, word salad. Numbers can't push his rhetoric. Construes disagreement as semantics. Okay, so what do I have to say about Roderick and Samantha? Well, uh, give me a second here. This is what I have to say about these two individuals. They're the ones who created all this nonsense, about all this language, this poppycock language that these people use. And so, yeah, I have a problem with it because, these individuals have filled the world with their jargon, carry a force, carry an interaction, transfer information. How do you transfer concepts? How do you carry a force? I mean, on the back. So they have all this language, This fellow today, in fact, we'll be talking about momentum, carrying momentum. How do you carry momentum? Momentum is already motion. How do you carry motion? How do you carry your run? How do you carry your swim? How do you carry your fly? Jesus. I mean, they have all this irrational language that they've created, and he complains about me saying, "Hey, Bill, you're changing the words." No kidding. Yeah, we got a problem with the language of mathematics. Okay? And so he says they don't do rational definition. What they do is operational, also known as functional definitions. And they look. This is what he says. Mathematics uses operational definitions. Yeah, that's what they do. And you look it up. An operational definition defines scientific concepts in terms of what? Of the operation used to prove them. So yeah, the guy waits till the end of the show to tell you what he talked about. So he mentions a word. He says, black hole is an object. He goes in there, talks 2 hours, and then at the end of the show says, well, an object is what I just explained. Oh, yeah, no kidding. What was it? I missed it. The way we do it in science, we define the words up front, the critical words up front, so that then people can follow the presentation. And these people say, no, wait till the end and you'll find out through the operational definition, through what we explained, what the definition was. So, yeah, operational definitions are irrational. And when you look at the Stanford Encyclopedia of Love of Wisdom, they call it philosophy, but you don't find the word philosophy defined in the Stanford Encyclopedia. And that should be the first word they should define. And again, it shows how the whole establishment is screwed up. If these people haven't defined the word philosophy, what kind of encyclopedia is the Stanford Encyclopedia of Philosophy? So yeah, it's love of wisdom. That's what philosophy is. And yeah, operationalism is based on the intuition that we do not know the meaning of a concept unless we have a method of measurement for it. Yeah, so it's nonsense. What these people have is absolute nonsense. They say we measure, and based on what we measure, that's the definition. Yeah, and that's how they ended up with particles at two places at once, and one particle entangled with another one affects it without any mediator. Yeah, sure. And that's how they also ended up with warp number lines. Okay, so he continues, says, mathematical language avoids private semantics. Okay? Yeah, the definitions aren't private. They are introduced and anyone can challenge them and provide an alternative. Okay? So, anyone can present a definition. You don't like the definition, you had better have a better mousetrap, period. That's the way it is. Bill replaces mathematical definitions with what? Personal definitions. No, I replace them with rational scientific definitions. You don't like the definition? Again, all you have to do is challenge it and provide an alternative, a rational one. That means you're going to have to defend it. Okay? And what is a definition? A scientific definition. It's a limitation placed on the extent or usage of a word. Okay, so we had to define the word definition because people say, well, let me look it up in the dictionary. And what you find in the dictionary, definition is equal to meaning, and meaning is equal to definition. So they use these synonyms. Turns out that meaning is not a definition. Meaning is what the jury gets. Definition is what the prosecutor, issues. Okay? Prosecutors give definitions. The juror receives meaning. That's how it works. Okay, it's on the receiving end. Anyways, rational definition that can be used consistently, rationally, scientifically. That's a scientific definition. That's a rational definition. Okay, if you can use it in a consistent manner. Okay, and these people don't have that. They have, for example, just to put an example, light is both a particle and a wave packet. All three of them, all of the above. So what is which is the true mediator of light? And if you don't define the word object, you will never answer that question. A proponent of the scientific definition is required to defend his or her definition and show that it is rational. And you can't use any of these. Tradition, arguments of tradition, authority, or democracy. You can't say, well, everybody at the math club voted for it. Or that I got it from my teacher and he's an authority, he's got a Nobel Prize. Or this is the way we've always done it, it's in the dictionary and blah, blah, blah. You can't use any of those arguments. You have to defend your theory with something other than tradition, authority, or democracy. Okay? So you should be able to rationalize your definition. So don't tell me that my definition, or it's my private definition, my personal definition, or that you don't like my definition. You have to look at the definition, say what's irrational about it. Irrationality. For that, you need to define what rationality is. Another word that nobody's ever defined. No one knows what rational and irrational is. And again, it's on and on and on. We have to define all these words. Okay, so here he points out that my definition of object is shape. Okay, Bill's definition of object is that which has shape. Absolutely, every object in the universe has shape, and that's the only universal property of all objects. Okay. Physics cannot be explained without objects. You need an object to do physics. So it's the first word that a physicist needs to define. And it turns out that they have all these librarians, language majors, ontologists, philosophers, whatever they call themselves, right? And they're doing the definitions for physics. So the physicists say, hey, you want to know what an object is? Look it up in the dictionary. Yeah, who did the dictionary? Who wrote it in there? It was one of these people who has no stake whatsoever in the word object. They could define anything in there. In fact, you have people like Russell, right? And Bertrand Russell, and he said any word that can fit as a subject of a sentence. That was his notion of what an object is. And that's absolutely not true for physics. Okay, you can't put the word motion or the word orbit as a noun in physics. You cannot put it as a subject of the sentence, not formally. Okay, those are motions, those are verbs, as far as we're concerned. And no one has ever defined the word object scientifically. So, it's like we're breaking new ground here. We have a new definition because there's never been a definition. We have the everyday definition, the definition we find in the dictionary, which is not scientific at all. Okay, and so what you find in the dictionary are all irrational definitions. Not one of them meets the criterion of what science requires, that it can be used consistently, rationally, scientifically. Okay, it's because of that he thinks that field, the big word of mathematical physics, the two words, energy and field, but we're going to look at field first. Field is a concept, and he thinks it's a physical object. Yeah, and here it is, Bozo Joe, misconception. Fields are just numbers. Energy, momentum are concepts. Concepts can't push, okay? He says that's a misconception, all of those three. And he says fields are degrees of freedom. What is a degree of freedom? I mean, a degree of freedom is a physical object. Degrees of freedom is just the amount of variables that you can vary. In whatever you're doing. It's got nothing to do with physics. Okay, he says fields are degrees of freedom in modern mathematics, right? They carry what? Energy. How do you carry energy and momentum? How do you carry them? What kind of language is that? What kind of sense does it say to carry? And then it turns out that he believes that energy and momentum are physical objects. So he says he's carrying like you carry a rock. Okay, that's how he's using it in this sentence. Okay, that's what's objectively there, written. And he says fields, energy, momentum are physical. Field is the thing that pushes. And, what is field? Right at the bottom says, evaluate each location and object to pull. Absolutely. You cannot pull unless there's an elongated object. And he says, interactions are what? Via fields. Yeah, because he uses this word field as a physical object. He says he's going to do the pull with fields. Okay, so not only does the field go outward when it's going outside your flashlight, light is two fields, electro and magnetic fields going outwards, but then he's got these fields also pulling somehow. The fields, I guess, in the number lines known as space-time. So you have these number lines, and they're made of fields, and you can pull on those fields, and that's how you produce pull. See, that's how easy it is. Forces arise because the field configuration with the objects closer has lower energy. That's not an explanation. That's a description. But he doesn't understand the difference between a description and an explanation. The fact that you're telling me that it has lower energy, that's not the cause of pull. Okay? And he says the force is the gradient of that energy. Yeah, force and energy are not physical objects that you can use to explain how one object pulls on another. When the farmer pulls on a donkey, we call that force, we call it pull. That's what you have to explain. In this case, you're using a rope to pull on the donkey. What are you using to pull when you're using a word in mathematics? What's the mediator? We want to see a physical object. And he's using words such as force and energy. He says it's a gradient, or words lower energy. Yeah, so you have lower energy, and that's why it pulled, because we have lower energy. That sounds like, when they say that space-time, when the four number lines bend, that's gravity. Yeah, sure, bend the number lines, okay? So he says no action at a distance. Yeah, it's action at a distance as long as you use concept. You need to put a physical object. You have to draw it. You have to illustrate it, okay? Opposite poles approaching reduces field energy. Opposite poles? You mean positive against negative? North against south? What is this? A civil war of some kind? How does north pull on south? How does positive pull on negative? That's what you got to explain. What's the physical meaning of those terms? And he said the resulting force pulls them together. Yeah, I mean, you can explain anything when you use abstractions. We're talking about real objects. Put an object, a mediator, then we can visualize what you're saying. You cannot say that positive attracts negative, north attracts south, or whatever. Oh, that's garbage, nonsense, poppycock. Okay, and where do you get all this stuff? Well, here's another boson in the establishment. His name is Sean Carroll. Okay, and he says we don't use particles in quantum anymore. We use fields. And let him tell you in his own words. Okay, I mean, I'm not going to put words in his mouth. Let him tell you with his own words that quantum is dead. Quantum means discrete particle, little ball. That's no longer true. Now they use fields for everything. What is a field? We don't know. It's a concept. And what is a particle? It's the vibration of field, which we don't know what it is. Okay, so listen to him. Okay, here it is. Give me a second here. Here it goes. Listen to him.
What do quantum fields in a vacuum look like? Empty space.
Just looks like empty space. It's as empty as it can be.
But there's still a field. It's just...
Yeah.
What is nothing?
We now know that, the reality of our best way of understanding the world is through quantum fields, not through particles. So even the electron, not just gravity and electromagnetism, but even the electron and the quarks and so forth are really vibrations in quantum fields. So even empty space is full of vibrating quantum fields. And those quantum fields in empty space are entangled with each other. This location in space, there's a gravitational field, which I can detect by dropping something, right? I don't see it, but there it is.
Well, it would be a miracle. It would be a total miracle if he could see a field. I have trouble seeing concepts, quite a bit of trouble, in fact. So yeah, this is where these people get the idea. They say, oh, it's a field. Oh, okay, that explains everything. Now we know it's a field. And here's another bozo. His name is Arvin Ash. And this clown says, fields are everywhere, okay? Virtuals pop in and out of existence. Yeah, by what mechanism? Please explain. And so he has a field that vibrates and a little bump comes up. And he says, that's a real particle. Okay, what's the fake particle? Those are the virtual ones. Okay, so here goes. Listen to him. Let me get this guy out of there. Give me a second here. This is what he says about fields, okay? He says that fields exist, so please believe him. Listen to him.
In these turbulent seas, a large wave can be created. These are the real particles. The fields are always there and exist everywhere. Now, although they exist everywhere and you can't see them, they are not nothing. They are teeming with virtual particles. These are particle-antiparticle pairs that get created and destroyed. They come in and out of existence constantly.
That's not magic, right? They pop in and out of existence. I mean, how is this different than the old time religion, where they say, oh, the spirit came in and appeared and he talked to me and then he left. I mean, these people are doing religion. They're not doing science. None of that is science. That's why they say we can't find meaning in quantum. What's the underlying meaning? Of course they'll never find meaning because they're using concepts to represent, their physical interpretation. Their mechanisms are done all with concepts, with mathematical concepts. And they say, we understand it. Yeah, you understand it, but you have no meaning. That means you don't understand it. You can mathematize it. You can describe it mathematically. You give a name to that quantitative description, but that doesn't allow you to tell me what exists out there and how it works. And that's where the problem is, at the micro and macro level. Okay, what is it that these people need to do with fields? And here, let me give you an example here. This is what they have to do. This was what they were supposed to do all along, all the way beyond Faraday and some of these other gurus of science, alleged gurus of science. And here are fields. Okay, you have two wires. The one on the left, current is running into your eyes. Okay, and you can see the pattern is that's got that figure 8 in the center. And as you work out, finally you see the envelope. It just goes around both wires. Okay. How about the repulsion wires? Here you have one electricity in one wire coming to your eyes, the other one going away from your eyes. And when they're in opposite directions, you have this repulsion. And here you can see that the iron filings, when you sprinkle them on there, they have these patterns where it's like, I call it the two rollers of one of those old washing machines where you put the whatever piece of cloth that you want to dry, you put it between them. You can see it's squeezing whatever goes between them. That's what those two things are doing. What I'm saying, these things are things in motion, which whatever you see there, those lines of force that are moving or moved at least at some point, the iron filings, those are sweeping around constantly. They're sweeping around. So this is my interpretation of that, what's really happening. Okay, there you see the figure 8s on the left-hand side, and you see the rollers of a washing machine on your right-hand side. And what you see here is that whatever's spinning around there is going clockwise on both wires on the one on the left, and going clockwise and counterclockwise on the ones on the right. Okay, and so here's the summary of this thing. Okay, so that you can compare them. The ones on the top represent the two things going in the same direction, both clockwise, right? I got to do it the other way around for you to see it. Clockwise like that, right? And the other ones clash. They hit against each other and they're squeezing whatever's in there between them. Okay, that's what I'm saying. That's what you're staring at. That's what we see it. This is what we see. What we don't see is what's happening inside there in that region. Okay, and that's what we needed to identify all these centuries. Okay, and here it is. Okay. Here you see it in motion, what the field is. It's made of all these lines that are moving around. And we're saying it's the threads of the ropes that are foundation of our theory. And in the case of the clockwise and clockwise, the attraction, the one on the left, they're all moving in the same direction. And the reason they're attracting is that as one comes up, the other one comes down, and they interlock. They attach to each other slightly. Very tenuous friction, Mother Nature's friction, I call it, because it's at a level that we cannot even imagine. And gazillions of these threads are sweeping around. We're looking at them sideways, right? That's what's pulling the two wires together, electric wires together. Here on the other side, you have them going one in one direction, the other one in the other direction. Now the same threads are hitting against each other, pushing each other away. And that's the mechanism we propose. And people might say, well, where did you get this idea that, that there are things swinging around in there, some threads or whatever? They think those lines of force are just abstractions. It turns out the field they think is real, it's an object, but the real object, which are the threads that are moving around, they think those are concepts. They say, we just use them to explain, but they're not really there. And boy, they're wrong, completely wrong. It's the other way around. That's one issue. And here you see it. Good old Faraday said, I cannot conceive curved lines of force without the conditions of a physical existence in that intermediate space. He said those lines of force are real. Those are the real things, not the field. The field is the concept. And there we have good old Maxwell. He said, what is a field? The space in the neighborhood of electric and magnetic bodies. In that space, what? There is matter in motion. There's some exotic matter in motion that we cannot see or touch, but there is some matter in motion because of the table. Length is what you got out of it after you measured the table. Okay, first you make a standard, you call it the meter. You measure 2 meters. Did you measure meters? Did you measure length? No, you measured table. Okay, let's get that right. Okay, we can only measure objects. Okay, let's move on to the second issue. And it's this warped light, this bent light. Really, it's bent. It's not even warped. It's not curved. It's not what is it? A continuous curve. It's a straight line. It's like this. It's sharp. It's broken. That's how it is. And here, let me give you an example of what I'm talking about. Okay, you see 2 prisms. And you can see as soon as it goes into the prism, it bends the light somehow inside the prism and bends it once more when it comes out. Okay, no matter which way you go. Okay, so that's what we're trying to explain. We're saying, why does light bend like that? What causes it? And again, we can't use refractive index to, anytime you use refractive index to explain this, you have a mental retard. That's what you have. A person who doesn't understand the difference between a description and an explanation. Refractive index is a description. It's not an explanation. Okay, it's when you divide, the speed of light, for example, in a vacuum, and you divide it by the they calculate this through angles, but it goes through for example, prism made out of some solid material, and light bends. So they calculate the angle. They say, okay, light travels slower. That's their conclusion. Okay, and so they have all these angles. They have them mapped. They call that series of numbers refractive index for every single material out there. Okay, that's how that is. So you cannot say the reason it bent is because of the refractive index. Okay, no, refractive index is the result of a measurement. Okay, so you can't use refractive index to explain anything. Anyone who does so doesn't know the difference between a description and an explanation. Okay, so the other day I gave a little introduction on bending of light. What is bending of light? Why does it? What's causing light to bend when it goes into a prism? And I said, well, these are some of the parameters you should consider. Okay, if you're trying to zero in on the mechanism. Okay, here it is. One more time. Okay, you have straight light, and then you have the bent light. Okay, and the question is, why doesn't light continue straight? what's stopping it from continuing straight? And does it? Maybe it continues straight. We don't see it, but we see the bending of, the colors that show up at least in the prism. So that's one issue you got to think about. Does light travel straight? Can we talk about straight light? Or does light bend? Like, Einstein said, light curves around space-time, and it really doesn't curve. He didn't know the language. Einstein was one of those people who also, created a ridiculous language that we have today. And, you can't talk about curving of light. What you have done, if you're talking about photons, the photons were deflected because you were talking about motion, not about bending or warping or curving something. It's not curved like a banana, or a hammock. No, what you're saying is that the little photon turned a corner. That's what you're saying, went around. And the next photon is behind it. So light is traveling, in curves, what we call curvilinearly, right? And so that's not straight. So the question is, does light always travel straight or not? That's one issue you got to ponder, right? Another one is the angle, the incident angle, primarily. If it's at 90 degrees, right, with respect to the edge of the prism, is it the same up? Is it the same from another angle? You got to look at the angle, the incident angle, right? And also the angle coming out. Density of the material. Everybody says, well, the density stops light because a denser material, slows light more than less dense material. And I gave an example that is not true, okay? And here, let me put that one up there again real quick. And density of olive oil is less than that of water, but it has a higher refractive index than water. So you cannot use really density. It could be a factor, but, I think we have to rule it out. Density is not the primary factor. And so when they talk about, the fact that light travels slower through more dense material, there's proof, evidence that it's not true. Okay? Olive oil has a higher refractive index, meaning light is slowed down more, using their terminology, but it's got lower density than water. Okay, so just keep that in mind. Density is not the factor, or at least not the primary factor, right? And then we have the quantity of material. And by quantity, I mean, like here you have a prism, right? And, when you go to the top, there's more material going in that direction than if you go through farther down in the prism, right? So the question is, why is it always red on top and blue on the bottom? It's always like that, and the question is it because red has to go through less material and blue somehow through more material? Does that have anything to do with it? So we're not talking about the density here. We're talking about how much material light has to go through. Okay. And then you have the molecular structure, of the thing that it's going through. Like, what is the molecular structure of glass, of air, of water, and so on? All these media through which light has to go through. Okay. Okay, so what's the explanation of the establishment? Let's get that one right out of the right out of there. They have no clue. They have absolutely no clue why light bends. Okay, and here let me just put that on. This is from the AI, so you want to consult it, you can consult it. I asked them the question: why doesn't the beam refract in different direction, right, when entering a prism? I mean, why does it go upwards or downwards or in a different direction? Why does it go, in that very standard direction that it always goes through? And this is the answer that the R2D2 gave me. He says, a light beam refracts and bends when entering a prism. Yeah, no kidding. But the degree of bending depends on what? The angle of incidence and the prism's properties. Okay, let's find out how. As a beam of light enters the first phase of the prism, it moves from the less dense medium, air, to a denser medium. Well, yeah, we just showed that that's not universal, okay, at least. The light bends towards the normal, Okay, if the beam enters at a perpendicular angle, 90 degrees to the surface, right? In other words, it's straight ahead, right? Perpendicular, right? It slows down, but does not change direction. Why? Because there is no change in what? The angle with respect to the normal at that point. That's not an explanation. Okay, you don't say that the reason light bends or goes straight or whatever, it's because it's somehow related to the normal. That's like saying the angle changes. You know, you haven't explained anything. That's just a description. You're saying the angle changes. Yeah, we know the angle changes. Why? What's the cause? The physical cause. It says, for all other angles, the light bends towards the normal. Again, that's, we know that. Don't tell me what I know. Is there an echo in the room? What is it? When entering a denser medium like glass and away from the normal when exiting. Okay, again, that's just a description. They haven't explained anything. So they didn't answer the why. The question is a why question, meaning cause, a mechanism. And that's not what they're saying. They're giving you a description. They say, we answered the question. No, they didn't. When the light exits the prism from its second phase, it travels from the denser medium glass back into the less dense medium. At this point, it bends away from the normal. All those are descriptions. Not one of those is an explanation. And let me tell you why they cannot explain this. They talk about the speed. They say the speed, like it hit a brick wall, so it's going slower. And again, we can all understand you're going with your car and suddenly, you're going through water, a ton of water there. It slows your car down. And then when you're past the water, you go fast again, right? And so this is what they're saying. You go into a denser medium and suddenly you're slowed down. Well, that ain't true. It can't be true that you slowed down. And the reason is very simple. They're using photons. They're using particles when they're giving you that explanation. So the first thing you have to show, right, is that you can explain all kinds of phenomena with particles. And it turns out particles cannot explain a single phenomena using light. You can explain a single one. I mean, you want to explain the slit experiment. They say the particle is at two places at once. Yeah, that's not an explanation. That's cheating. That's magic. You can't say that that's an explanation. And again, all explanations involving, for example, wavelength, right, and frequency, they have nothing to do with particles. Particles have nothing in common with wavelength. You cannot reconcile them. So anything involving wavelength, like, Compton wavelength and so on, you can't use the particle. Particles are out of the question. So first you got to tell me what light is, what the mediator of light is, and you can't use particles. So you cannot say that the particles suddenly encountered a wall and they go slower. And then you say, well, it's the wave. The wave goes in there and the wave gets crunched, right? And it's squeezed. You can't say that either because wave is not a physical object. The wave of what? You got to tell me what the object is that mediates light. If you can't do that, you can't even start your presentation. We shut you down right there, take the microphone away from you. You got to tell me what light is. Then you can give me an explanation about speed. But these people say, the frequency remains the same, but the wavelength is crunched because it suddenly hit a brick wall, right? And so the wavelength is crunched, but the frequency continues being the same. And so that's why light goes slower. Not because the frequency changed or got longer or whatever. No, frequency remained the same. What changed was the wavelength. And that's artificial. I mean, that's, again, a Ptolemaic explanation. That's not the way you explain. If you want to explain, you need to first identify the physical object. Only then can you explain. They haven't been able to identify the mediator of light in the last 400 years. That's why they cannot explain. That's what they use, refractive index, and they say light slowed down because they have no explanation. They have no. Those are not explanations. They're only explanations if you can justify that light is mediated by particles. And you can't say that they're mediated by waves because transverse wave is a concept. It's not a mathematical concept. It's not a physical object. There's no physical object called a transverse wave. Okay, bunch of vectors. That's what they are. Okay, so here we have a prism. Okay, and you can see that the light. I like this picture only because the white light coming from the left kind of came from above, but it wasn't exactly what I was looking for. And I can't find on the internet people who do this right, especially in real time, with a real experiment. Okay, so I have problems right now trying to figure out how light still behaves when it goes through a prism. Okay, here, let me show you how I modify this picture. This is how I modified it here. Give me a second here. The one on the top, okay, I made it come, I exaggerated, made it come from the top. And the question is, does the color coming out of the prism go upwards? Or does it go downwards as you see on the right, upper right? Or if it comes from the bottom, do the colors go upwards or do they go downwards? I mean, this is what we need to figure out. And it's very hard to find someone who did this with actual prisms out there. And so, I couldn't find one. I'd really appreciate anyone who can find, an example of any of these. I need all 4 examples to find out, which way light is going. Okay. So, unfortunately, I was not able to resolve that issue to my satisfaction. Okay. Okay, so what did Newton do? Well, he took 2 prisms and he put them back to back like this, okay? And he said he was able to produce white light back out again. So even though white light came in and then turned into colors, then those colors, when he got them back out, he got it back into white light, okay? And here's the beam. Well, let me show you here what I did here. Let me get this one smaller. Okay, and what I did here, just to show you something that I put, the one on the left are not straight up and down. The edges of that are not straight up and down. The reason I did the one on the right, I just twisted it a little bit so that it's straight up and down, because now it looks like a thick glass. That's all it is. And the question is, does light go in those directions that you see there? Does one white light go straight through? Does the other one go and curve around like that and then come out the other side upwards, okay, in colors? Okay, so anyways, just to show you that, we need to figure out what light is doing. Right now it's very hard to tell because people put a lot of stuff on the internet, especially on YouTube, but they don't do the experiments that they should be doing. They just say, oh, look how nice this is. I can see all the colors and so on. Yeah. We need something a little more, that enlightens us, that we know what's going on. Okay, so here it is. We have 2 prisms back to back there. And if you shine incident light through there, you have transmitted light and reflected light. Okay, you have one going in one direction, the other one in the other direction. And what's sending that light? Well, the atoms. The atoms are doing their quantum jump. Okay, they're being stimulated and they're retransmitting or relaying the light forward or downwards in different directions. Okay, so here's a real live case. Okay, let me get this one out of here. And you can see they've shown a light, but I don't see colors there. Okay, so I don't know if we produce colors there or not. Again, a lot of people are not focusing on the issues that we need in order to answer the question. I don't have enough equipment to do a lot of this stuff, or the high precision cameras to be able to, take pictures of these things. But maybe someone can, pitch in. Okay, so let's move on here. Here we have good old Fresnel, Augustin Fresnel. He was a French guy. He studied light quite a bit. And he did an experiment that gives us a little bit of insight into the molecular structure of material. Here you have this famous experiment where he's shown a light and he put these polarizers. Polarizer and analyzer they're called, but they're polarizer. And it turns out that when light is shown through this material, it reproduces it faithfully back behind it. In other words, light goes to one atom in that material, and it retransmits that same signal behind it. Okay, but what it does, it chops off, according to mathematics, according to Fresnel, in fact, chops off the horizontal component and only allows the vertical component to go through. That was his assessment, and that's the one we have even to this day. And then when you put a second, in this case the analyzer, right, horizontal, it kills also the vertical component of light. So the question is, is light comprised of only electric field when it goes past the first polarizer? I mean, we only have what? What kind of light is that? It doesn't have any horizontal component. So yeah, kind of weird, the explanation. And the worst part is that when you put a third analyzer behind that second one, you put a third one, it reproduces the beam. And the question is, how did it do that? I mean, I thought the beam was extinguished at the second polarizer. How did we reproduce it after we put a third one in there? So, these people, cheat a lot when they're doing all their explanations. They cheat a lot, or they leave a lot of information that is critical to understand what's happening in there. But the point here that I'm trying to make is that the molecules, the molecular structure of the material is important. It has to have a bearing if these Iceland spars or whatever material you're using as a polarizer, can retransmit the signal behind it, like if it was straight ahead, right? And so it is retransmitted. If you turn it sideways, then light does something different. That's the point I'm trying to make. And so yeah, the material, the molecular structure of the material is important too. And so let's look at that for a second here. Here you have a molecular structure, for example, of glass, right? SiO2. Okay, what happens? We're going to shine a light through there, okay? And here it is. Okay, we're going to shine a light, and we're going to assume this is the prism, so it's kind of slanted on the sides, okay? And the question is, does light travel straight ahead, like that center yellow line, all the way across? Does it zigzag? And it's just that we don't see it. Does it zigzag or go in all different directions? And the one we always see is the one we see at the bottom. In other words, the one that turns into colors and then comes out the other end also at an angle. That's the one we see. And we say, well, hold it. If every atom in there is sending light in all directions, why don't we see not only the light colors, forget about that. Why don't we see light in every direction? Shouldn't that whole thing be illuminated, And so, again, we need to find out if the material itself has something to do with it, okay? If the molecular structure of the material. And here's the rope version of that, okay? Let me show you the rope model, okay, so that you can get a hang of it, okay? It's different theory altogether. We're saying all atoms in the universe are physically interconnected. Hydrogen atoms, right, at that level, right? Uranium has 92 hydrogen atoms essentially, and what is it, like 143 or 146, depending on if it's 235 or 238 isotope, neutrons. So it's got 143 neutrons. You got to treat each one of those as one atom, because neutron essentially is an atom in our model. So you're talking about 240 plus, what is it? Can't remember now, 235 and 238 hydrogen atoms. That's essentially what a uranium atom is. That's how much matter it's got in there, okay? But each one would have one rope attached to every atom in the universe, okay? So that's the way you have to look at this. One hydrogen atom attached to another hydrogen atom, irrespective of what it belongs to, an atom or a molecule or a material or whatever, okay? It doesn't matter. Every atom, every hydrogen atom is attached with one rope only to another hydrogen atom. That's the assumption, okay, the hypothesis. Okay, so here we have one side of the prism. We're going to have one atom here in air, and the other atom right at the edge of the prism, okay? And we're going to assume there's no space between them practically. In other words, there's no other atom between these two. Okay? It's just direct connection. There's no atom between them. Okay, so this is what we're gonna assume here, and we're gonna have white light. White light is composed of different colors of light, meaning that each one has a different wavelength. So the one on the top has longer wavelength than the one on the bottom, if you can see there. Hopefully that's more or less visible. Okay, so the red one has longer wavelength, the blue one has shorter wavelength, meaning link length. The links are shorter, you have more frequency for blue and less frequency for red. Okay, so that's what I'm showing there. You see the slanted surface of the prism, so you have one atom, really two atoms, because one atom is going to send one frequency, one link length, and the other one's going to send another one. Okay, so one atom sends the blue, the other one sends the red. Okay, and they're pumping, they're doing their quantum jump, and the ones in the prism, they're relaying that same red and blue signal to other atoms inside the prism. Okay, that's what I'm showing there. Let's look at the other side, the right side. This is the left side of the prism. Let's look at the right side of the prism. Here it is. Okay, again, we're showing two atoms only, and only red and blue, right? So one has shorter wavelength, which is the blue, and the other one has longer wavelength, which is the red. Okay, frequency is inversely proportional according to little c. C is equal to frequency times wavelength. If the link length, right, the wavelength is longer, hopefully the frequency is shorter, meaning lower, right? You have lower frequency. That's what we're showing there, okay? And there you see the slanted surface of the prism. That's what we're trying to illustrate here. So you see the two sides there. Let's now put them together, okay? Here it is, the two sides of the prism. Okay, so on the one side you have two atoms pumping through ropes to two atoms in the prism. One has, it's white light because it's got all the colors. Here we're showing only red and blue, okay? That is being retransmitted by the atom in the prism to the other side. And the other side receives a red and a blue, and from there it's pumping those same frequency and wavelength, link lengths, to atoms again in air, okay, for example, or whatever environment you've got, okay? So that's what we're showing, okay? Now the question is, why does it bend? And the answer is, we don't know. So after all this, I'm just telling you that we don't know. First of all, you know, the establishment has no idea, again, because they talk about speed. But even if we concede speed, let's concede speed. Okay, let me give them speed. So the speed changes. The wavelength is shorter, and the frequency remains the same. Why does it bend in a given direction? Why does it go upwards? Why does it go downwards? Why does it go all over the place? And that's the question nobody can answer. And that's the question I asked the AI, and he can't answer it, the little bot, the R2-D2. Why can't they answer it? Because they don't know what light is. In order to answer that question, as a minimum, you need to know what light is. You need to have a mediator for light. You can't use particles, okay? Because they can't explain anything regarding light. Not a single phenomenon can be explained with discrete particles. And you can't use waves because it's a concept. You know, a bunch of vectors, fields, you know, those are concepts, mathematical concepts, so you can't use those. So please be creative, brainstorm, find out what is the mediator of light. And once we get that, then maybe we can explain why it bends. I cannot tell you exactly. I've been looking at this for years. I got it back again because the person asked a question about 2 weeks ago. But I've been thinking about this on and off over the years. And now, I decided to look at it again. I still can't have an explanation for it. Why does a rope in a given direction, why is that one the one that we see? And by the way, let me show you this, because this is the how you see it from your point of view. Why do you see blue and red light and so on? Because you've got your eye right there outside of the prism, right? And all these atoms that you see there, they're not only relaying signals to other atoms inside the prism, they're also relaying through ropes the signals to your eye. That's why you can see all this stuff. because they're all relaying through a bunch of, air molecules and atoms. They're relaying the signal to your eyes. Okay, so that's why you can see all this stuff. You're looking at this from afar. But the question is, why does it bend? That's the question, and the answer is we don't know. We have no idea why that specific bend, why certain angles. They say refractive index is so much, depending on the material, if it's dense, and depending on the incident angle, the angle of incidence of light. Yeah, but that's a description. You haven't told me the why. Why does it bend in a given direction at a given angle? Why does it bend in the opposite direction? To say it's close to the normal, farther away from the normal, you haven't explained. All you did was describe, and that's what all these people do. So the answer is we don't know. Okay, and as far as I know, nobody on Earth can figure that problem out. And all I can tell you is you got homework to do. And yeah, anybody can help out, be great. I can only tell you that if we use a rope as a mediator, you have a good chance of being able to explain it, because the rope is taut, always taut, never bends. Okay, ropes don't bend. It's the threads that bend. Okay, people confuse thread with rope. Okay, the rope is always taut, and the question is, if it's taut, the signal always travels straight. Okay, for our macro world, that is straight, even though it's really a torsion that we're seeing, and the atom is pumping and sending that torsion to your eye as well. Why does it go in a given direction, not in a different direction? That's the whole question. The answer is, I don't know. Okay, so I hope you're satisfied with my answer. Okay, let me move on to the main topic of today, the main course. Okay, and that's the bonds, James bonds. What are all those Jimmy bonds that quantum has? And let's start with this fellow so that we can put it in the right context. His name is Derek Muller, and he shows that molecules can be attached by a hydrogen bond. Okay, and so let's just quickly cover that base so that you know that that's the case, that's how it's being explained, that a hydrogen bond can bond two molecules, really one atom in each molecule, but it physically has these two molecules attached to them, or it could be atoms as well, right? Here it goes.
Rings of 8 sulfur atoms. Look for places to attach. They grabbed onto a carbon atom from a rubber chain, breaking its double bond and attached itself. Then with another free bonding site, it grabbed onto a carbon atom from a different rubber chain, breaking its double bond and linking the two rubber chains together.
So what's the point? The point is these are physical bonds, okay? They're binding, they're attaching, they're holding two molecules together. So we're not talking about an abstraction, okay? That's the point I want to make. And one of the problems we got is we don't see these bonds in the standard model. I've never seen a bond in there, a little line, dotted line or otherwise, right? So I don't know what all these bonds are, but it turns out there's more than just a hydrogen bond. And here's a summary of them. These are the James bonds, the Jimmy bonds, okay? We have all these secret agents that we know nothing about. One is a hydrogen bond, another was a covalent bond, ionic bond, and finally the metallic bond. Maybe they have another bond out there, another Jimmy bond running around for all we know. So what are all these bonds? Well, let's go through them kind of quickly here. Here's the covalent bond, okay? Let's start there. And you can see what it is. Really, it's the merging of shells, of orbitals, of energy levels. That's what they're merging. Here's the hydrogen, okay? And now we're going to have the oxygen there. And look, the two hydrogen molecules to build water, right? And they just merge their electron shells, their energy levels. And I thought an energy level was a region. What do you mean you're going to merge two regions? What does that mean? You're merging two concepts. So this is not an explanation, but this is the best they've got. And this is simply a description saying, the two regions merge, and because of that, you can find electrons in that region. And so what? How does that maintain the bond? How does that physically keep the two molecules, these atoms together? And they haven't explained that. They just say mathematically, that's what we verified, with math, that the electron shells, the energy levels merge. That's it. That's the covalent bond. Okay, now let's look at the ionic bond. Okay, here's the ionic bond. And how does this work? Well, one of these, the sodium and the chlorine, right, they lose their marbles. The sodium's going to lose its marble, right? The other guy's going to pick it up. And now because of that, one is charged, the other one is not. And so what happens is one becomes positive, the other one negatively charged, right? Because one's got one electron too many. And so the protons are now coming together, okay? Because one, or the atoms really, they're coming together. Why? Because one is positively charged, the other one's negatively charged. Okay, so what does negative and positive mean? What is this positive and negative nonsense? And they don't have an explanation for that. Again, this is just a description, a mathematical description saying, look, when this guy loses his marble, for some reason it becomes positive, the other guy becomes negative, and because of that, positive attracts negative, and that creates what we call an ionic bond. So now you know. Okay? See how easy it was? Yeah, this is not an explanation. It's not a physical interpretation. Okay, you haven't understood anything about the micro world that Mother Nature runs out there, because you can't visualize what they're saying. They're just saying the orbitals come together. Okay, so what's an orbital? Well, it's a region. You mean two regions come together and they merge and they keep the two atoms bound to each other? Regions are concepts. So you can't say, you got to put a physical object. They're not used to putting physical objects in physics, in mathematics, right? Physics, yeah, we are, but not in mathematics. And then here's the metallic bond, which is a sort of covalent bond, okay? And here you have an atom, right, one of those. And what they do, they have all these electrons running around for whatever reason, right? And they say it's just running around all these electrons. It's an electron soup, so to speak, right? And it keeps those atoms bound to each other simply because all these little marbles are running around. And again, if they're running around, how do they keep them together? And it's a kind of merging of the kind of like a mixture between ionic and covalent bond, where these atoms, these protons, right, the center nucleus of these atoms are attracted to others simply because all these electrons are running around. Okay, so that's it. We don't have an explanation of any of this. This is just descriptions. They're saying they're running around because, if they're all discrete particles, you cannot talk about attachment or pull, which is what they're trying to describe here. You cannot describe pull, explain pull, if everything is a loose particle. That's why you cannot explain anything in Mother Nature's world, micro world, with particles. Particles are dead. And that's why good old Sean Carroll says, hey, we use fields. We don't use particles. Why? Because fields are supposed to be these extended objects. They think they're things. And so they say they extend forever to infinity. Oh, okay, so now we can talk about action at a distance through fields. There is no action at a distance, right? And they use this concept called a field to do the binding and the pulling and all this other good stuff, attraction, right? Okay, here's the hydrogen bond, the one we're going to talk about today. Okay, so here it is. These are the hydrogen bonds. And they put a little line there, usually dotted line. What is that line? I didn't see it in the standard model. I don't know if you've seen it. Please let me know. And they just put them by hand. They just say, oh, there's a hydrogen bond. What is it? What is it made out of? If it's going to bind two molecules together, there you have water plus NH3, right? Pulls them together and holds them together, the hydrogen bond. How does it do that? Two water molecules, the H and the O, are bound by, held together, right, by a hydrogen bond. So we're not talking about, an abstraction here. They're saying that this thing holds them together physically. Okay, so what is it? Please draw the stick. What stick is that? And where is it in the standard model? And they just say it's a hydrogen bond. That's it. That's all you'll know about a hydrogen bond. And they're going to try to define it, but again, using concepts. So, we don't need that. We need for them to point to that stick and say, this stick is a hydrogen bond, which is what they illustrate, okay? Okay, so here we have the hydrogen bond again, okay? That red one there. And so what do? Well, they go in there and they put a little dotted line. We say, well, what is that line? I mean, you can put anything you want in there. Well, what is that dotted line? And what we're saying is that this is what it is. It's a rope that connects one of the hydrogen that comprises oxygen, because remember, oxygen has 8 hydrogen atoms at least in it, right? And one of those balls, one of those fuzzy balls that makes up the oxygen atom, which is kind of like a molecule in itself because it's got 8 hydrogen atoms in there. One of those is connected to the hydrogen atom of another water molecule. That's what's happening, okay? And so that's our take on that. Here's another vision of that. Okay, you have the oxygen there on the left, and you have a hydrogen on the right, and we're saying that one of those hydrogen that makes up the oxygen atom, almost a molecule, you could say, right? Because it's a molecule in itself. But one of those balls is the one that's connected to the hydrogen on the other side. Yeah, so it's hydrogen versus hydrogen. That's all we have there. A single rope, and that's going to be the hydrogen bond. Okay, it's a physical bond. Is it attached? No, it's not attached. Remember that the 2 threads, of a rope, right? Here we have a rope, and the 2 threads, one forms the electron shell, the other one goes through the center and forms the proton star. That's encapsulated within, by the threads that make up the ball of yarn that is the electron shell. Okay, here we have water, okay, and you can see how, these molecules, they're running loose in that pool of water. And what you see is that what's merging is really the energy levels. That's what's merging. What is that blob that's around the 2 hydrogen atoms? And they say those are the energy levels. What they're blending is their energy levels. So that's kind of weird because energy levels are regions, and they turn them into physical objects at their discretion. When they define the atom, they say, well, it's the region where you can find the electron bead. The bead supposedly is the physical object. The region is only where you can find it. It's a where, not a what. And then they have all these wheres, and they merge and they blend and they form molecules. And you say, oh, did the region blended? What nonsense is that? And the electrons are running in there loose. Again, how does one electron affect another one if they're all discrete entities? And so that's when they say, well, it's got a field around it. What is a field? What is a field? A concept. There's just a bunch of values saying, well, around it, it's got all these values. Yeah, it's a region of values. That's not a physical object. Okay, so here we have the covalent bond between 2 hydrogen atoms, and when they merge, they form that figure 8, typical figure 8, okay? Covalent bonding of 2 hydrogen atoms to form a hydrogen molecule, and they form that classical figure 8 pattern, okay? And the question is, what's happening there? What's actually happened in this covalent bond? And here we have an explanation from the rope model, okay? We say the 2 are coming together and they merge. Remember, the rope, as they come together, they become shorter and shorter and shorter until, one of the threads of the rope moves into the shell of an atom. The other one goes right through to the proton, to make the proton. So it's all made, the whole system is comprehensive in the sense that, you have a rope, and the rope gets shorter and shorter and shorter, and the rope makes up the electron shell as well as the proton star. When they come together, one simply unwinds into the other. That's what's happening there. So the blending of the shells has to do with the fact that, it's the same material. It's all done by this thread. It's a simple system in that sense that, it's all mediated by the threads. Okay, and what you see there, the ropes extending from each of the 2 atoms, Okay, every atom in the universe is attached to our two atoms there, our two target atoms that we're using there, right? Okay, so that's the model for covalent bonding. And here we have, here, let me put this up here. Here we have another version of that. Okay, that's essentially what's happening to the rope between them. Okay, that's our model. That's what we're saying is actually happening. Okay, simply the rope gets shorter and shorter until they merge into each other. And why? Because the shells and the protons are made of the same threads that make up the rope. Okay, so that's essentially our explanation for it. Very simple. I think baby stuff. It's just you see it, you understand it. Hopefully, I mean, I don't know. You might have questions. In fact, I'll open the place for questions in a minute here. And here's the final one, which is the ionic bond. And what is it? The shells are spinning. Remember, the electron shells spin around the nucleus. And one's spinning in one direction, the other one's spinning in the opposite direction. Okay, so one is going clockwise, the other one's, they're both going in the same direction, both going clockwise. So when one comes down, the other one comes up. And that's what the attraction is. It's a physical attraction between threads. And you have gazillions of threads swinging around. Remember, the shell is built out of every thread that comes from every rope in the universe. So you got gazillions of threads that build up these shells, and they're moving in the same direction. When one comes down, the other one comes up, and there's your attraction. That's what we call an ionic bond. Okay, that's why these atoms are attracted to each other. Okay, very straightforward. If you can illustrate it, you can more or less understand it. You just have to follow. Now, do you believe in it? We don't care. Belief is part of religion, whether you believe it or not. Here we try to make it understandable so that you can look and say, I understand that. I don't agree with it. Or the other guy says, I do agree with it. That's belief. We can only show you the mechanism. Okay, I'm going to open up the floor for questions. Anyone who has questions on any issue of physics or the material we covered today, go ahead. I'll give you 10 seconds. Remember, it takes about 10 seconds for me to receive it, for you to receive the answer. Okay, so we don't have instantaneous transmission. Oh, been cut off. Okay, disconnected. Okay, so we'll see you next week.